Hey everyone, welcome to our next video. This one is going to be continuing the identity section. Come over to our notes. Oh, it'll load. There we go. This section is 6.2, which is the sum and difference identities. When it comes to using identities, there's really so many ways that we can use them, and there's different kinds of questions that you'll see. So we're going to have a few different ones in here. The first thing we're going to talk about is the sign, addition, and difference formula or identity. So this is sine alpha plus beta is equal to, and I'm just going to give you the identity at first, sine alpha cosine beta plus cosine alpha times sine beta. The sign difference identity is sine alpha minus beta, and this would be sine alpha cosine beta minus cosine alpha sine beta. Now these identities, if you are taking my class at least, these are given to you on your test. So we'll have an identity sheet. I'll go ahead and show you that right now. So I'm going to pull it up on our canvas. Sorry y'all, I thought it was already pulled up, but it wasn't. This is our Canvas page. And if you click right here under Test 2 info, I've got this PDF. So these are the identities that you'll be given on Test 2 if you're taking my class, of course. So right now we're working on this top section right here, the sum and difference. The next section will cover the rest of the identities. So you don't have to memorize these. These are given on a formula sheet. Come back. Notes are gone. There we go. So let me show you we'll just kind of jump into an example of one of the uses for something like this. So example 1, I'll say find the exact value of sine 75 degrees. So the main issue here is when we're looking for like exact values. So that's like kind of like the table information and like unit circle stuff. So if I say like 30 degrees, 45 degrees, 60 degrees, and then we've got sine and cosine. This is 1/2, root 2 over 2, root 3 over 2, root 3 over 2, root 2 over 2, and 1 over 2. The issue with 75 degrees is it's in quadrant 1, but it doesn't have, right, it's 75 degrees from 0. So it doesn't have a reference of 30, 45, or 60, which means we don't know it. But what we can do instead is we can find two angles that we do know have a reference of 30, 45, and 60, and we can use those instead of 75. So we can use, so I'll ask you and you can answer it, what are two angles we can use that are in that table that add to 75? My hope is that you've said 30 and 45. So sine of 75 is equal to sine 30 plus 45. Now this is not as simple as just saying, okay, let's do sine of 30, sine of 45, and then we'll add them together. Not that easy, unfortunately. that's why we have the identities. So if you want to add two angles like this, we need to use the other half of this identity. So I'm treating my alpha like 30 degrees, my beta is like 45. So I'll have sine 30 degrees times cosine 45 degrees plus cosine 30 degrees sine 45 degrees. Sine of 30 is 1/2. Cosine of 45 is root 2 over 2. Cosine of 30 is square root 3 over 2. And sine of 45 is root 2 over 2. So when I simplify this, I get square root 2 over 2 plus square root 6 over 2. Oops, sorry, not over 2, over 4. When you multiply across, the denominators multiply. So this will give me square root 2 plus square root 6, both over 4. Be careful, I almost made a little mistake there, but I usually catch them pretty quickly when I make those little mistakes, but it's easy to make, so be careful. Right, so the whole point of this was we're trying to find like a weird angle, so we try to use two angles to add up to that instead. Let me go ahead and do another one of these, like with a sine one. I'll also say that you can do this with the difference identity. I'll try to show you an example of that as well. So let's do another one of these. It's in the same vein, so I'll just say find the exact value of sine trying to think of one that would be good. We can do 255. Now the issue is if I go and I graph 255, so it's in quadrant 3. This is 180. So 255 is 75 degrees away from 180. So it does not have a reference of 30, 45, or 60. So what we do instead is we can find two angles that add up to 255 that we can use instead. And this one we're going to have to not necessarily only stick to the first quadrant. We're going to have to look outside in another quadrant. You have options for this. So 255, you can, pause the video, try to think of angles that you can use. As long as the angles that you pick have references of 30, 45, and 60, you're good. So for example, I could do 210 and plus 45. I could do another one, 225 and 30. I could do see, some people might say stuff like this. They might say, okay, I'm going to do 180 and 75. Well, the issue is you don't know 75, so that's not a good one. Or some people may say, okay, I'm going to do 195 and 60. Well, the issue is 195 doesn't have a reference of 30, 45, or 60. So again, not a good one. So you want to pick ones that have references of 30, 45, and 60. 210 has a reference of 30, and 225 has a reference of 45. You could also use the subtraction identity. A lot of times students will ask me like, well, you use addition a lot. Like, when do you use the subtraction? I'll be honest with you, it's not as common. Most of the time we use subtraction when it's like a small angle. So if I did like sine of 15 degrees, I could do 45 minus 30 or 60 minus 45. But you really can use either one you like. So for instance, I could do 300 minus 45, and that would give me 255. So that's an option. My personal preference, I usually end up using the addition a lot. So I'm going to do sine 210 plus 45. And so I use my identity. So this is going to be sine 210 cosine 45 plus cosine 210 times sine 45. Remember, 210 is in quadrant 3 and it has a reference of 30 degrees because that's how far it is from the x-axis. So sine of 210 is the same as sine of 30, which is 1/2. But we got to be careful. We're in quadrant 3, so it has to be negative. Cosine 45 is root 2 over 2. Cosine 210 would be square root 3 over 2, negative because quadrant 3. And sine 45 is root 2 over 2. So when I simplify, I get negative root 2 over 4 minus root 6 over 4. So this is negative root 2 minus root 6 over 4. Sometimes I get questions about like simplifying the radicals and stuff. You can only combine radicals with addition and subtraction if they have like the same, it's called their indice, but their index. So like if it had said like square root 2 plus square root 2, you can add something like that or subtract it, but you can't do square root 2 and square root 6 because the inside of the radical is different. Let's go ahead and do some cosine ones now. So we can also have the cosine sum and difference identities, so I'll write those out for us. Again, these are on the identity sheet, so you don't need to memorize them. And the difference, so these are the cosine sum and difference formulas or identities. And I'll do some more examples of basically the same thing, but we're just doing it with cosine now. And I can also do some more of sine, we can do lots of things. So example 2, I'll say find the exact value of cosine 195 degrees. Now also remember, anytime something says exact value, we're not trying to use decimals or anything because that's not exact anymore. So we're trying to use like square roots and stuff. So I'm looking for two angles that can add, or we could also subtract to get 195. Usually, if it's bigger than 30, 45, or 60, I'm probably going to add, but you could also subtract. I will do one where we like have to subtract in a minute. 195, I know I could do 135 plus 60. That would work because 135 has a reference of 45. I could also do, let's see, what's another option? You should pause and think of some. 165 and 30 won't work because 165 doesn't have a good reference. I could do 150 and 45. That's also another option. If you want to do one with subtraction, I could do 240 minus 45, or I could do 225 minus 30. So again, there's a lot of options. I prefer the addition ones, just because there's no, I don't know, they seem a little easier, I guess. So cosine 195, instead of doing 195, I'm going to do 135 plus 60. I use my identity, so I have cosine 135 times cosine 60 minus sine 135 sine 60. 135 is in quadrant 2. It has a reference of 45. So cosine 135 would be root 2 over 2 negative. Cosine of 60 is 1 over 2 minus sine of 135 is root 2 over 2, and sine of 60 is square root 3 over 2. Get negative root 2 over 4 minus root 6 over 4. So negative root 2 minus root 6, both over 4. We can do another one with cosine. We can do more sine, either one really. I guess let me do one in radians. Sometimes that can be a little hard to work with when we do radian ones. So for my next example, I'll do example 3. Oh, I'm writing black. I'll say find the exact value let's do sine, well, we'll do another cosine. Cosine pi over 12. Sorry if the audio was a little bad for a moment there. I don't know how sensitive this microphone is, but my son was crying in the background. He's just waking up from a nap, so. When it comes to angles that are in radians, when we do stuff like this, my personal preference is to just change that angle into degrees. I just think it's a bit easier to like find two angles that will add or subtract to it when you deal with degrees. And it's just because in radians, you got to deal with the fractions, and fractions can always be a little difficult for students. I'll show you how to do this one in radians, but again, I will also show it in degrees just so that you can have that experience. So for pi over 12, if I look at pi over 3, pi over 4, and pi over 6, so this is 60 degrees, 45 degrees, 30 degrees. If I make these have denominators of 12, this would be 4 pi over 12, 3 pi over 12, 2 pi over 12. To get to pi over 12, I will have to use some kind of subtraction. I can't like add any of these and get a 1 here. But I can do either. So for pi over 12, I can either do 4 pi over 12 minus 3 pi over 12, which would be pi over 3 minus pi over 4. Or I could also do 3 pi over 12 minus 2 pi over 12, which would be pi over 4 minus pi over 6. So these are my options here. So this would be cosine. I'll just use the first one. I'll do the 4 pi over 12 minus 3 pi over 12, which is really pi over 3 minus pi over 4. I'll use my identity, so I get cosine pi over 3 times cosine pi over 4 plus sine pi over 3 sine pi over 4. Cosine pi over 3, remember pi over 3 is just 60 degrees, so that would be 1 over 2 cosine pi over 4 is square root 2 over 2 plus sine pi over 3 square root 3 over 2 sine pi over 4 root 2 over 2. So for my answer here, I get root 2 over 4 plus root 6 over 4. So this is root 2 plus root 6 over 4. If I had wanted to just switch that to degrees, pi over 12 times 180 over pi is 15 degrees. So I could have done this same work, but just said, okay, cosine 15 degrees, and then we can, this would have been cosine, I could do 60 minus 45, and all the work would have been exactly the same. Cosine 60, cosine 45, plus sine 60, sine 45. We would have gotten the exact same answer. So that's why I personally would probably, I would just change my radians to degrees anytime I'm trying to work with that, because you get the same answers and it's just a little easier to work with. At least for these, I think it's important to know the radians, like the 30, 45, and 60, knowing that that's pi over 3, pi over 6, pi over 4, pi over 3 in order. I think it's important to know those and to know the ones that actually have references of pi over 6, pi over 4, pi over 3, that are on unit circle. But whenever we do the weirder kind of angles, I think it's fine to switch to degrees. I'll do one more of these that are like find the exact value. Let's do another sine one. And we'll do 5 pi over 12. I'm also going to make this a negative so we can see what happens with that. You have like a negative angle. First thing I personally would do if I ever have a negative angle is I would pull it out to the front if it's sine. So remember, sine is an odd function, so that means that negative can pull out to the front, and then it can just kind of hang out with us the whole time. So I have this negative sine. I'm going to switch to degrees, so 5 pi over 12 times 180 over pi. I get 75 degrees. Maybe I should have done cosine, because technically we already did a sine of 75, but that's okay. Now I have the negative outside, so it'll be negative. For 75, you could do 30 plus 45. You could also do a subtraction. So let's see. Let's do like a subtraction one just because. So 75, I can do 120 minus 45. Let's do that. I'm going to do sine 120 minus 45. I have negative sine 120 times cosine 45 minus cosine 120 sine 45. One 20 is in quadrant 2. It has a reference of 60. The sine of 120 is the same as sine of 60, which is square root 3 over 2. Cosine 45, root 2 over 2, minus cosine 120 is negative 1 over 2. Sine 45, root 2 over 2. So I get negative root 6 over 4 plus root 2 over 4. So this is a negative root 6 minus root 2 all over 4. And if you look earlier, like my very first example we did, for sine of 75, I got root 2 plus root 6 over 4. So this is just the negative version of that, because basically all we did was negative 75 degrees. Remember that you could also add 2 pi to something to no longer make it negative, so you don't have to use the even-odd identities, but I think they're nice to use. Next, let's look at tangent addition identities and difference identities. So tangent addition is tangent alpha plus tangent beta divided by 1 minus tangent alpha tangent beta. The difference identity is tangent alpha minus tangent beta over 1 plus tangent alpha tangent beta. My preference when it comes to doing tangent is not usually to use one of the difference identities, and it's just because I personally, so this is my official example 4, I personally actually like the half angle identity to use for tangent, like exact value type problems. But there are reasons that maybe you would like the addition or difference one. The only thing is it's a little hard to simplify. So sometimes you have to be careful about that. So for this one, I'll say find the exact value of tangent. We'll do do sorry, y'all. I kind of have to think of these sometimes, because sometimes I write them in the notes, but then I end up doing one. Like the one I have in my notes for a tangent was negative 15 degrees, but we already did a 15 degrees. So I like to, mix it up a little bit. I'll still do a negative one. Let's see that if I do a negative. I can do 285. Let's do that. There's really only so many of these you can do. It's not like an infinite amount of them. So tangent is an odd function, so that negative can pull out to the front. So this is the same as negative tangent 285. You also, if you want to, you could change this and say this is tangent. You could add 360 to negative 285, and you could work with 75 degrees. That's also perfectly fine. That's probably the easier route, but I've already done a bunch of stuff with 75, so I kind of want to do the harder version. So I'm going to work with this 285. You guys can do the 75, and if we get the same answer, then you know you're good. But I should do the harder one. So I have this negative for 285. Let's see. I'll do 240 and 45 could work. So let's just do that. So I'll have tangent 240 plus 45. And I'm going to plug it into my identity. And this negative is just going to be out in the front the whole time. This is like my alpha. This is my beta. So tangent 240 plus tangent 45 divided by 1 minus tangent 240 times tangent 45. Get negative tangent of 240. So remember, 240 is in quadrant 3. It has a reference of 60. Tangent of 60 degrees is square root 3 plus tangent 45 is 1. And also quadrant 3 for 240, so tangent's positive. Then I have 1 minus tangent 240 is square root 3 times tangent 45, which is 1. So here I get negative square root 3 plus 1 over 1 minus square root 3. To simplify something like this, you have to use the conjugate. So again, I'm just going to keep that negative out in the front, but I am going to multiply by the conjugate, which would be 1 plus root 3. So I get negative square root 3 plus 1 times 1 plus square root 3 divided by 1 minus square root 3 times 1 plus square root 3. I get square root 3 plus 1 plus square root 3 plus 3. Make sure I wrote all that right. So square root 3 times 1, and then 1 times square root 3, 1 times 1, square root 3 times square root 3. I did a little bit of a weird order, but at the bottom I get 1 minus square root 3 plus square root 3 minus 3. I'll come up here. At the top I get 4 plus 2 root 3 divided by 1 minus 3, which is 2. This will give me 2 plus root 3, and then I have my negative I can distribute in, so negative 2 minus root 3. And just to check, if I put this in the calculator, I get negative 3.73. If I type in tangent negative 285, I have, my calculator tells me it's positive 3.73. So did I miss a negative or anything anywhere? Let's just make sure that I typed everything in correctly. I am using a phone calculator, so never really know how accurate those are. Sometimes I always regret making stuff up whenever I type it in, and if there's something I messed up somewhere, I'm like, oh, what I get for making stuff up. Well, there seems to be something wrong about my negative in here. I may just have to leave it and, oh, I see what it is. I found it, guys. Found it. This is why sometimes, I'll tell you this, it can be nice to have your calculator to kind of check you. You might have already found it, but it took me a second. When I did this 1 minus 3, so this step to this step, this should have been a negative 2. So then what would have happened is when I divided by that negative 2, this would have become negative 2 minus square root 3. And then I distributed my negative, which turns it into positive 2 plus square root 3. So sometimes it can be nice to have your calculator just to check your final answer. Sorry about that, y'all. I am no stranger to making those simple kind of, sign mistakes and stuff like that. That's always, sometimes I almost like that I can make those mistakes because then I get to show you what not to do, teach you how to be careful. Alrighty, well, let's do one more. Well, we won't do another tangent one. In the next section, we'll do more with tangent, and we'll use the half angle, which is a little easier to simplify, actually. So for example 5, I do want to do another one with sine and cosine, but this one looks a little different. So this says find exact value, sine 25, cosine 35, plus cosine 25, sine 35. This one looks like one of our identities. So it looks a lot like, if I'm letting this be alpha and this beta, alpha, beta, it looks a lot like sine alpha, cosine beta, plus cosine alpha, sine beta, which is the sine addition identity. So sometimes you can actually go from the longer side to the shorter side. So this is equal to sine 25 plus 35, which would be sine 60, sine of 60, square root 3 over 2. So I just thought I would do that one real quick because that one's like an example of going from the bigger side to the smaller side. But a quick example. This next example is a little bit different. This one requires us to use some triangles. So it says find the exact value of sine alpha plus beta if sine alpha is equal to negative 3 over 5 and cosine beta is equal to negative 1 over 3 with alpha in quadrant 4 and beta in quadrant 3. This is a little different of an example. We're still finding exact values, so you're probably going to have some square roots at the end of this. Not guaranteed, but it's really often. So. But the interesting thing about this one is it doesn't actually give you any like actual angles to work with. It gives you sine of an angle, cosine of an angle. When you see stuff like that, like if you see something like this where it's giving you like sine of an angle, you're either using identities only or you may need to use a triangle to come up with other values. So first I'm going to write out sine alpha plus beta. So I'm going to write out my identity. Okay, so I have that first. So it gives me sine of alpha. So sine of alpha, I already have it. It's negative 3 over 5. I also already have cosine of beta, which is negative 1 over 3. It gave me those values. I don't have cosine of alpha or sine of beta. But I can go get those values by using triangles. So for my alpha stuff, it says that alpha is in quadrant 4. Remember, it should touch the x-axis. And if sine of alpha is a negative 3 over 5, sine is opposite over hypotenuse. This means my opposite side is negative 3, my hypotenuse is 5. If I want to do cosine of alpha, I need adjacent over hypotenuse. I can use Pythagorean theorem to find that missing side. So I have negative 3 squared plus x squared equals 5 squared. 9 plus x squared equals 25. X squared equals 16, so x equals 4. And it would be positive because we're on the positive x-axis. 4 over 5. So now I have my cosine alpha is 4 over 5. Now I need to go get my sine beta. So let me use another color for this. I'll do purple. So for sine beta, I'll write it right here. I have cosine of beta. Remember, cosine is adjacent over hypotenuse. It also says beta is in quadrant 3. So I have quadrant 3, beta, make my triangle. Adjacent side is negative 1, hypotenuse is 3. I can find my missing side using Pythagorean theorem. So I get 1 plus y squared equals 9, y squared equals 8. Be careful when you take this square root of both sides. We're in quadrant 3, so my y should be negative. So this is going to be negative square root 8, which can simplify to negative 2 root 2. I'm not super picky if you leave it as square root 8, but we should simplify it. If that's something you forget on a test or something, I wouldn't really take off for something like that, but it is good to do it. So I get negative 2 root 2. Now, I'm looking for sine of beta, so remember sine is opposite over hypotenuse. So this is going to be negative 2 root 2 over 3. So I wrote that into my identity now. So just a little bit of a recap before I keep going. We wrote out my identity. I already had sine of alpha, cosine of beta, but I needed cosine of alpha and sine of beta. And I used triangles to get those values. Be careful. If it doesn't actually tell you what alpha and beta are, it just gives you like sine of alpha, cosine of beta. You may just be using triangles and identities. You might not need to actually find an angle here. Sometimes what students will do is they'll write me stuff like this. Here, I'll write it down here. They'll say like sine negative 3 over 5 when they plug it in. The problem with this is not an angle. So it shouldn't go in those parentheses. This is so bad. But it always leaves people stuck because then they're like, I don't know what I'm supposed to do after that. Well, you kind of messed up like line one. So kind of, I'm not surprised you didn't know what to do, uh, you can't really work with that. So just be careful. I'm going to simplify now, so I get positive 3 over 15 minus 8 root 2 over 15. So I get 3 minus 8 root 2 over 15. And we can just leave this as it is. I really do like this one. You just have to be careful that you don't like plug this in as alpha or this in as beta. You have to replace the whole thing. I just have one more example for this section, and this one is a verifying problem. So it says verify the identity. And this one is sine pi over 2 minus theta is equal to cosine of theta. Our first step here is we want to work with one of our sides. I usually tell you that the harder side is probably the one to start with. That's not like the one with more stuff. That's not always the case. It is in this one though. So I'm going to start with my left-hand side, which is sine pi over 2 minus theta. I see that I'm subtracting things, so this should bring me to look at my sign difference identity. So like hypothetically, I'm looking at this on the test, I would see that subtraction and I would say, okay, that probably need to use an identity because otherwise I don't know what to do. So I would go over to my identity sheet and I would look at the identity that I see. So my sign difference is that a minus b. So I would go ahead and write my identity in. So I have sine pi over 2 times cosine theta plus, minus cosine pi over 2 sine theta. Sine of pi over 2 is 1 times cosine theta minus cosine pi over 2, 0 times sine theta. Well, anything times 0 just goes away, it's just 0. So I get cosine theta. So that equals my right-hand side, so I am done. I like this one because I feel like it looks way harder than it actually is. Like once you get going, you're like, oh, okay, that's it. But it always seems a little scary, when you first look at stuff like that. So that's it for this video. Just kind of a recap, there's a lot of different ways that you can use identities. Sometimes it's to find weird angles. Sometimes it's to like use triangles and then plug that into the identity. It really just depends, just depends on the question. But test 2 is all about identities and equations, so you'll definitely be using that identity sheet. I hope y'all have a wonderful day, and I will see y'all in the next video. Bye-bye.